Progress.
All right, guys, let's get started. Um, yeah, so we're recording, right? Yeah, some questions. So the first question is, when is the exam? So if you guys want to know when the exam is, you can always just go to Google. You type PNW final exam schedule, and it should take you to something like this. And take a look in here. So this is for fall and spring. So we meet on Tuesdays, so we have to find Tuesday, and then our class starts at 4. So that, yeah, Tuesday, 4. So our exam is on Tuesday of finals week from 5 to 7 p.m. This is the time that we have been given. We have to stick with that. Got it? Any questions on that? All right, so your exam is in 2 weeks, right? 2 weeks from today, essentially. Remember, it's similar to the other 2 exams. It's comprehensive, so anything that we've covered from the beginning of the semester until the end. It's all the cryptography that we covered. Yeah. So any questions about that? It's closed notes, but you're allowed your cheat sheet. You can write whatever you want on it. All right. Yeah, same format. 3 problems, 3 code type things, 3 essay type things. Explain. All right. And of course, you can expect maybe, the things that we've covered, Diffie-Hellman, elliptic curves, quite a bit there. And then the basic things, symmetric and asymmetric encryption. Okay? Yeah, so so that's the exam. Today is the last lecture. So today we're doing our last lecture. You have one last homework, which is the OpenSSL, right? So I think that I don't remember when that's due, but that's your last homework. If you want a bonus lab, there's the Big Num crypto lab. So you can tackle that one, but you have to do it on your own. And the key there is the same concepts, nothing new, but it's in C, C++. And so it's using, as the name implies, big num, so really large numbers. And so it needs to be very efficient, and that's, you guys know that performance is key in cryptography. So that's the idea. Today we're doing, as I said, our last lecture, which will be on Bitcoin, blockchain, all of those ideas. And it's just kind of a fun exercise going through some of the concepts, going through some of the code, just to show you how it works. There's nothing really new as far as algorithms or things like that. It's everything that you guys are familiar with, but just as a type of an application. So remember, this is more of an applications type. So I usually end the course with this one. If you guys are interested in this topic, there is a blockchain course, but I believe it's offered in the summer. That's all blockchain, I believe. All right. The scavenger hunt is on Thursday. I've already started preparing that one. So I've done 2 of the 4 encryptions, and I haven't decided if I'm going to do a 5th one. If I do, it would be either elliptic curves or Diffie-Hellman. So make sure to review that. Okay. But as I said, the encryption is very simple. What you did with PyCrypto demo or PyCrypto Dome, your demo, that's AES, RSA, that whole pipeline, right? So make sure you understand that. I provide the code, by the way, so it's not like I suggest you have your code, like on your GitHub, etc. But usually I give you the code also, so essentially it's about, plug and play. Does that make sense? So I'm really not asking you to modify the code that much. You may need to change parameters, little things like that, values. But definitely understand the concepts of the files, very much like how you did the PyCryptoDome lab. Make sense? So there's usually one encryption, which is just that, like that. There's going to be one that's going to be the RSA one, break RSA. You guys know how to do that with FactorDB, right? Or you could use the quantum computing program, but probably FactorDB is faster. There might be a manual one that you have to compute by hand, like some of the ones that we've done in class where you kind of solve for something by hand. At the end of the day, every one of these is going to give you a password or code or something. And then once you have all the codes, you put them together and you have one big code, and that's going to do the final decryption of some secret message that I've hidden. Okay? That has never happened. Okay, yeah, and so any questions about usually it's something, as I said, you could solve in 15 to 20 minutes if you know what you're doing, so it's not meant to be long, okay? But I'm going to give you the full hour and 40 minutes of Thursday to solve it. Questions? Essentially, you have to give, like in previous quizzes, you had to give me the answer, right? I usually take a sentence or a quote from a movie or something like that. So that's what you have to give. All right, got it? All right, so yeah, so that's Thursday. And then, yeah, the last thing is the project. So the project is due a week from today. You'll start doing your presentations, right? So you'll come up here, present, and, the group, everyone should present. Just explain what you did, if there's an algorithm or technique or whatever it is, and then do the demo. Either code or you installed some kind of program in Linux that does cryptography, like VPN or something like that. Any questions about the project? Yes, please.
Did we ever end up doing a hashing password cracker in class?
Password cracker. I don't know that in this class we did. I think we do that in 372, I want to say.
Okay.
But password cracker, not cryptography per se.
Using hashes.
Uh-huh.
The word list, hash out the word list, and then compare it with the hash of the password.
Don't we do that in 372? I feel like that's like the first lab in 372.
Okay.
And you took 372 with me. Yeah, I believe that's something we did in that class.
Okay.
Any other questions about the project? All right. Yeah.
What do you want to submit for? Do you want to submit like a research paper? Or?
No research paper. I usually just need some kind of a report that's evidence of your work for like ABET and all that stuff. So, like a lab. Screenshots, descriptions, things like that. It's not a research paper for this. All right? Good? All right, great. Yeah. I don't know, how are any of you taking 490 next semester? 490, is it too early, or some of you are? I do have a project for a kind of a 490, which is I want students to install locally something called N8N, which is a GUI, which you might like, not coding, but a GUI-based AI agents framework. It's extremely powerful, and so you can automate companies, activities in business. But it's setting up something locally and configuring that with templates. So what you do is you create templates of, this is my AI accountant, which works with my AI lawyer, and they interact together to produce reports, right? And so you install it locally. So if there's anyone taking a 490, that's a good project to consider, and quite a bit of work. But N8N is like a type of a future Excel in corporations. You know what I mean? Like, it's going to be tools like that are going to be very important for AI automation. Anyway, so if you're interested. So let's get started with the class today. This is our last lecture, and it's going to be, as I said, continue with applications, blockchain. So I just have a very simple script. So we are going to go back to our repo on cryptography here. All right, and I have this one, Bitcoin blockchain. So I have several ideas that we can talk about related to Bitcoin. I'm sure some of you have heard of miners, right? So this is a thing, like some of you may even have a GPU at home, right? Or or several GPUs, and you're mining the blockchain so that because it translates into percentage of Bitcoin, and that's money, right? So essentially, this is the very simplified, I should say, this algorithm that you see here of what mining is. And mining essentially is just taking a thing, hashing, and you continue to hash it and hash it and hash it and hash it, and you're measuring a type of a security metric that you have that you can calculate given that hash. And essentially, you want that value to be really low. So that's what mining is. You keep repeating this and calculating this number until this number is below a threshold. The moment you hit that, you've achieved a level of security that's desired for the blockchain. Do you see that? And so that then it's going to be accepted to the blockchain, that hash, because you found it. So it's essentially that. It's a calculation of hashes until you achieve, the desired complexity, security, whatever you want to call it. And then at that point, the blockchain would accept it. And, and by the way, all of you could be trying to do that, right? So all of you go for that same block. All of you start that task on your GPU, and you're just not succeeding, or your miner, whatever you want to call it, you're not succeeding. So you keep trying, that's why you want to be faster, more powerful, right? Because you want to find that number, that level of security before the others. Right? Because if, let's say you find it first and you submit it and boom, you get allocated some Bitcoin for your trouble. You see, and that's how people make money, because that Bitcoin, of course, you guys know, converts to money. Right? So essentially so that's this algorithm. It's like kind of an easy one. So we'll explore this one as far as the blockchain. And then I also have this Jupyter notebook here. And we're going to go through it just to kind of explain, this idea of getting the keys that you need to do, getting a wallet so that people can put Bitcoin into your wallet, right? So remember that it's, Bitcoin and the blockchain is a software, almost like a network type of a software that's distributed, right? And but essentially all of you would have an ID of some kind, and that ID is, accepted in the blockchain, and then there's transactions that can be done. Okay, so that's the idea. So let's start with this code on. This is a simple blockchain mining example, just to give us an idea. You guys understand what hashing is very well now, right? So variable length input goes in, and you get a fixed length output, right? Of a number, a sequence of characters. And, if you change one bit of it, it changes the thing completely. So that's essentially the idea. So we can see here a very simple example of, mining. So obviously you would install some software on your computer, you download from the web. This is just a standalone algorithm to kind of give you the logic. So in this algorithm, we will have a block class, which represents the block in the blockchain, which essentially just contains data. It contains the index of that block, and then it's going to keep track of things like something called a hash and something called a nonce, which is another thing that you're calculating. There's going to be a mine block function. There's going to be a function called create genesis block, and there's going to be the main execution. So essentially, the mine block function iteratively increments the nonce until the block's hash meets the specified difficulty. All right, and this can be measured in the number of leading zeros that it has. All right, so based on that, you can determine how secure it is. Okay, and so you're essentially, just think of it that way, right? So you calculate hashes over and over and over, and then finally you're measuring the security of it. If it meets it, great, it's accepted, right? So you're trying to be very secure. This is the verification step. This is just to create the blocks. The blocks, essentially, in its simplest form, is just a list, right? So just think of it as a list of hashes, potentially, or a list of objects, right, that hold data in it, and they represent the blocks in the chain. So it'll say something like, here is the index, here's the data, here's the hash. That's it. It's there out there in the internet. So anybody can look at it. That's the index. This is the data. But this hash, verifies it. It says, okay, the integrity of this is great. It hasn't been modified. It's very secure. So when you're creating the blockchain, which is this list of these objects, you start with something that's usually called a genesis block, right? And then from there, the next element in the chain depends on the previous one, right? So it becomes part of the data that you're hashing constantly, so that everything in the chain cannot be altered because they depend on the first one. All right. So Bitcoin is the first one, right? Satoshi something. He not even clear who he is, right? But they wrote a paper back in the day, and he invented, or he did the first implementation of these ideas. He owns, I think, like 1 million Bitcoin, and that's just sitting there. No one even knows if it's ever going to be cashed. It would be worth a lot of money. All right, and then the main execution, basically create blocks, mine a few blocks, and print the values. All right, so this is a very simple example. You can see here it's got a class called block, okay, which has a constructor, and then it has a calculate hash function. All right, so essentially you're just creating an object, a class that contains information about the block. Okay. All right, then you have another function here called mine block, so we will see that one. We have the create genesis block, which essentially just invokes the block class, and then we have our main example. All right, so let's take a look at how it works. So here we have, this is the main loop, so the everything begins here, right? So this is going to be a blockchain of just 5 elements. We create the genesis block. So how do you do that? You create, essentially in this example, a list called blockchain. And the first thing that goes into the list called blockchain is the function create genesis block. Do you see that? So now let's take a look at the function create genesis block. What does it do? It essentially instantiates the class block, and it provides a few values. So it provides a description. This is the genesis block, and this is essentially index 0, the first one. Do you see that? So let's go into block, this definition over here, and you can see we have that here, this class. So it takes an index, the previous hash, right? And the data that you're going to have in there, and some nonce, this other parameter that you're keeping track of. So this is, you guys are familiar with object-oriented programming, so this is just a constructor. So you have the index, you have the previous hash, which is passed here. There's nothing because it's the genesis block. You have some data that you provide, such as this was the genesis block. So these are things that you can write in there. You have this nonce calculation, which is 0 initially, a timestamp, and then you have a hash. Right? So everything is based here on the hashes. So calculate hash. So how do you do that? This essentially is referencing this function here. Okay? So what do? You guys know, we take in variable length input, hash it to produce fixed length output. So in this case, we take the index as a string, the previous hash, the timestamp, the data that you have in there, and the nonce that you have in there for this, and you concatenate all of it into a variable called data to hash. All right? And then once you have that, you just invoke hashlib SHA-256 or something like that, and you take data to hash dot encode, and that's it. You hash it. Do you guys see that? So it hashes. It's similar, to how we did, for instance, the public keys, right? And things like that when we were calculating signatures. So you calculate that hash, and that's it. So now this block has a hash value of itself, okay? And so that's done. So we've gone over block, we've gone over create genesis block, and we're done with this part of the code. So we have a blockchain with one initial block. Any questions? All right, so what do we do now? now we're going to move on. It's a chain, right? Block chain. You see, right? So it's a chain of blocks. We've created one. Now we're going to create the next set of elements in this chain. So we're going to need something called previous block, right? So that it follows the chain. So from the list blockchain, we just grab the first element. That's it. Quite simple. And then here we have a for loop. Now I'm going to create several blocks in the chain. And they're all related to previous ones, and all of them have their own hashes so that it is quite protected. So remember here, it's not confidentiality that we're looking for, right? It's integrity. Right, so you guys understand that. Also, authentication is going to be important as we get into the wallets and all of that, because you don't want people to steal your Bitcoin, right? So, but here it's really just about, I think it's called proof of work or something like that, and it's blockchain. They describe it as a ledger, right? So some people will say that. So transactions are done. Maybe I heard VeriSign. You guys, no, not VeriSign. Sorry, DocuSign. Or something, DocuSign, right? So the one where you get contracts and you sign them electronically. So they've already started to add some of those to the blockchain, right? Because then they just add that data, and then people go in, hash it until it meets a certain level of security, and boom, it's verified. And now people can look at these contracts, right? But they know that they have integrity, so they're secure. All right, so here we have an example of hashing several blocks. So I'm going to do, this is just an example, very simple, but it gives you the idea. So this is a range of 4 additional blocks, okay? So here we're going to create a new block, okay, that's going to be added to the blockchain. You see blockchain.append, so it adds the new block as a second block, but how to add it to the chain, it needs to undergo the hashing, and it has to be the secure hashing, which is what gave birth to the blockchain mining. So here we have a function called mine block, and so essentially what it does is it takes the previous block, which if you remember, we grabbed it from here, so all the data there, including the hash, and then we provide some new data for it, such as block 1, right, data, right? And then we give it some value here. So now we go into the function mine block, and you can see this is some parameter relating to difficulty, whatever they're using. And so now you have the previous block, the data that you provided, so the current data plus the old block, right? And you have the difficulty. The concept is not that complex, right? It's pretty straightforward. So then what do you do here? You're gonna instantiate a new block, obviously this first block, not after the genesis block. And what does it take? It takes the previous block index plus 1, the previous block hash, right? And the data itself, right? So that's kind of what we had looked at before, index, previous hash, data. And so these is instantiated as a new block. There you have it, new block. Now it's data, but it's tied to the previous one because it contains the previous block's hash. All right, and then what do you do here? And it has an index that follows the previous index. So now here comes the loop, and this is the loop. It's the mining. So if you ask me where is the mining here, this is the mining, right? So you hear the word mining, and you're like, what are they actually doing on that computer, right? Well, this is the mining. The mining is what then? It's a simple loop, right? And what is this loop doing? It's essentially looking at the new block hash starts with, and this is the metric to measure the level of difficulty. So for instance, here this is implying a difficulty of 7 times 0. So it has 7 zeros in front of it. And that's an indicator of this type of difficulty. Do you see that? Yeah, so that's essentially, it's very hard to obtain that number, right? You just kind of keep trying and trying and trying and trying until you get it. And then when you meet that condition of difficulty, let's say 7 for the sake of argument, so let's say 7, so 7 zeros in front, boom, you succeeded. But otherwise, notice it just says while not. So if you haven't met that level of security, you have to keep doing the process. And what is the process that you're doing? You're calculating this nonce, which essentially is kind of keeping track of how many times you're doing this, right? And every time, what do? New block dot calculate hash. We already looked at that. That's essentially just taking all the data from the current one plus the previous hash and calculating a SHA-256. That's the famous mining, right? And so that's why people then have, buy GPUs and all this stuff, right? Expensive computers, because they want to do it faster, better, in parallel, however they want to do their algorithm, and arrive at a condition that meets this criteria, and boom. The second they do that, right, they say, okay, I found the hash that meets the condition, submit it to the distributed environment, and it'll be accepted. And if it's accepted, you have an account and all that stuff, then for your trouble, they'll pay you a little bit of money. It's funny how this works also. Different groups have different rates for what they pay. So you as a miner might go, this is 0.005 Bitcoin, this one's 0.003. Oh, here's one, 0.017, right? So a little bit more Bitcoin, so you're gonna go for that one. Because that may be more important for somebody. They really want to get on the blockchain for whatever reason, right? They have a motivation to have that security. And so they'll pay a little bit more to get into it sooner, and the miners are essentially the ones that decide, right? So if you're paying very little, like 20 zeros and a 1, no miner is gonna commit resources because they're spending, the GPUs, $5,000, all the electricity that they're spending, so it may just not be worth it for them. Do you guys see that? But that's essentially how this idea of mining works. Any questions about it? Make sense? All right, perfect. All right, so that's blockchain mining, the simplest algorithm, as I said. Remember that this is implemented. People build a distributed system, and they'll use these ideas. There's Bitcoin, Dogecoin, meme coins, I think, are a thing. Ethereum is, everyone can create their own thing, right? But they do it like this. So this is the algorithm for mining. All right, now let's go, and this one we'll do through code, so I'll open Colab and we can try it out there. But you can click on this Jupyter notebook that I put together here. It's mostly like notes and things like that that we can go over, but a lot of these things should be familiar to you. So we're going to be using the elliptic curve idea, right? So you guys, we've already done that lecture, so hopefully you guys remember the structure of the function, right? And we have to calculate some values, okay? And so there's going to be a secret that we calculate, then that's like a type of a private key, then a public key associated with that. And then also we need to create a wallet, and which is just an account. So it's just numbers that you have, and these numbers exist in this blockchain, which is based on the elliptic curve. So if you guys remember, I said, when we talked about elliptic curves, they're just functions, like a circle, right? We know that how to draw a circle as a function, and then we have points on that, right? So the points on that curve are secure. Anything outside is not. We also talked about how we have operations like multiplication, adding, but these are geometric operations specifically defined for these curves, right? So we also discussed that. So we'll see a little bit of this in this example today. All right, so let's, I'll open up Colab here. And we can probably just use it more convenient. You can also do this on Anaconda if you'd like, on your VM. All right, so let's take a look over here. So Bitcoin, and this is essentially just Bitcoin and blockchain ideas, some key concepts. You can find more information about this here at Karpathy's GitHub. So you can check that out. Yeah, so key questions. How does Bitcoin represent value? Okay, so the first one, well, it's like a currency, right? So it's one of the things. So first we want to generate a brand new cryptographic identity. So we're going to need to basically create something like a private and a public key pair. Okay, so we'll do that. Remember, we've talked about private and public key pairs and like which are used for asymmetric encryption. And I described to you guys there's RSA, Diffie-Hellman with elliptic curves, which is actually being used currently with TLS, right? The protocol of SSL. So that's kind of what we're looking at today. So Bitcoin uses elliptic curve cryptography. Okay, instead of something more common like RSA to secure the transactions. Okay, so that's one of the key foundations of it. There are several elliptic curves that have, well, there could be many, right? Many elliptic curves, but there's a few that have been studied. The Bitcoin curve is called the SECP 256K1 curve. Okay, so a lot of people will just go to that one because remember, you can just pick another point and now you have your own system even though you're using the same curve, right? So you need a starting point and then do all the operations to calculate the other values. NIST, the National Institute of Standards, publishes recommendations on which curves to use, but people prefer to use other curves like this one, the SECP 256K1, that are less likely to have backdoors built into them. You guys know in cryptography, you know, there's a difference between, you know, the math or the theory of it and the implementation of it, right? Or what people say about it, right? So some can be insecure, and if so that's why this one has been studied widely and is considered to be the most secure. Okay. So an elliptic curve takes only 3 integers to define. So we've already talked about elliptic curves, if you remember. So that's kind of what we're going to be doing today. So just simple examples. So let me add these libraries here. And these are just annotations and for definitions of data classes with a little bit better consistency. All right, so here we're going to need a few classes. We're going to define the curve, and essentially we're just going to define it by the parameters, right? And it's going to be a curve like we've defined in the lectures before. And so we're going to use the equation and the values to calculate what we need. Do you guys see that? It's essentially, as this implies, an elliptic curve takes only 3 integers to define, 3 numbers. So here we're going to illustrate how to do this. All right, so we're going to define the first class just to define the parameters of the curve. Okay, so here this is a class, object-oriented in Python, of course, and we're just going to call it curve. So this will define the elliptic curve over the field of integers modulo prime. So we're going to need to have these numbers. Points on the curve will satisfy this. And if you guys remember, I think we did this exercise. We plugged in values. It had to equal, right? It had to be 0 equals 0 or something like that. So this is the curve that I'm going to use in this example. Okay? So it's going to be y squared equal x to the 3 plus a times x plus b mod p, where p is prime. Okay, you guys are familiar with this. So we're going to need our a and b parameters and a p parameter, which is a prime number. Okay, so similar to before. So that defines some of the parameters. All right, that's just a class. So this class definition. So let's try an example here. So I'm going to create a Bitcoin curve with this approach. So notice here I'm going to instantiate a variable called Bitcoin underscore curve, and it's just of class curve up here, right? The one that I just defined. Notice here it says the SECP 256K1, that's the suggested elliptic curve that's considered to be secure, uses A equals 0, B equals 7, and so we're dealing with the curve that would be of the form y square x3, A being 0 makes this part 0, and the B is going to be a 7 modulo some kind of a prime number. All right? Any questions? So that's the equation and the values. All right, so here you can see the values. A is, these are expressed in hexadecimal, so A equals 0. You can see that there. This is 7, and this is just some prime number that I'm going to be using for this example. All right, so essentially all I'm doing is I'm defining the parameters, and then we're going to use these parameters in an equation that looks like this. Okay, so let's go ahead and so run that. Okay, so that ran. Good. All right, so in addition to the actual curve, we're going to define a generator point, which is just some fixed starting point on the curve cycle. So remember, it's like x and y, correct? Because it's a point, so it's gonna be like these two dimensions to indicate the coordinates in the curve. So this is used just as a kickoff point to start a random walk around the curve. So now remember that to move around the curve, that's where we have plus, multiplication. So we have operations, right? And for that, I'm going to have some functions in there. Very complex functions. I mean, we're, somewhat complex, right? But they're going to be there. This is mostly being done from scratch, so you can see everything, how it works. And actually, this one implements, I think, SHA-256 from scratch. So if you ever wanted to see that, it's here. All right. So we need a point to start this thing called a random walk, just essentially operations to move around the curve so that we can calculate, guess what, another point. And then another point, right? And that's the trick. The generator is going to be a publicly known and agreed upon constant that you're going to be using. All right, so now we can grab a point. So I'm going to define a class point for this so-called G. Okay, so class point, an integer point, x comma y on the curve. We're going to define the parameters that this takes is the curve itself, so the values of the curve, and the values of the point x and y. Got it? All right. So we're going to run that. So now let's try to instantiate a point G. So this is just an example, right? So you would pick these numbers. These are in hex again, and these are x and y, which define the coordinates of the point itself. And we're passing what? Bitcoin curve. What was Bitcoin curve? This one, right, which had where we defined the prime number and A and B. Right, so now we have the parameters of the curve and we have a point. Okay? So that's going to be our G, and there it is. Okay, so now we can do various things. You can see here, this actually we did by hand before with much simpler examples. And now I'm going to do this with code, but it's the same idea. We can verify that the generator point is indeed on the curve itself. So i.e. y square equal x to the 3 plus 7 mod p. All right, so here I'm just going to print the statement. So notice I'm going to notice how it works. So here y and x are this y and x, right? So so here y, the curve as we defined it, y, x, they're essentially the coordinates of the point itself. Do you guys see that? So that's what we're going to compute. So we print generators in the curve, g dot y squared, right? Minus x to the 3 minus 7 modulo Bitcoin curve dot p equals 0. So this has been rearranged, right? So the algebra has been done to be rearranged, to rearrange the terms. But essentially, it should say true if it is equal to 0, which is what we want. Make sense? So again, remember, Bitcoin curve dot p, that's the prime number. You guys know how to do modulus. We've been doing that since like week 2 of this semester, where we did the percentage in Python, and then we just have y squared minus x to the 3 minus 7. Okay? So when we run this, it says true. So essentially, we know that this point is on the curve. And that's like, okay, perfect. Now we know that from here, as a starting point, we can do the operations. We're going to get other x and y's, other points. And that's going to help us at the end of the day to compute yet another number, right? Very much like when you were calculating your public and your private key. And I think we did like, going back to the number operations with RSA, right? So P was 64, Q was, I don't know, 53. And then in the end, we calculated some values for E, N, and D. Remember? And, so it's similar to that. Okay, so now I've tested that the value is indeed on the curve. Now we can try a different one, some other totally random point that would not be on the curve, most likely. So what I'm going to do here, excuse me, is I'm going to just calculate random numbers to prove. So I have a random seed, I have an x and a y, and I just create guess or calculate a random number in the range from 0 to the p-value, okay? And from 0 to the p or prime number. So we can try, for instance, to look at x. You can see there's your number. It's a very, very large number, right? But that's your integer for x. Make sense? All right. So this number is, I've calculated these randomly, so they should not be on the curve. But that's what we're going to try to test now. So how do we do that? The same way. Going to do control copy here. Control V. So totally random point should not be on the curve. So y squared minus x to the 3 minus 7 mod prime number equals 0. So if it's not, that equality doesn't hold, then it says it's false, so it's not on the curve. So that would not be a point that we would use. Make sense? And so there's your starting point, and now we can start to calculate our other numbers to define what we need, right, for to start using the blockchain, to have an identity in the blockchain. Okay. So here we're going to have a generator. Okay, so we're going to take a look at this idea. Copy this. Okay, so I'm going to use a data class. So I have a generator over the curve. So an initial point and the pre-computed order. So I have, a point G, a generator point on the curve, and then N, which is going to be some way of calculating another number. So the order of the generating point, so it's going to be, essentially G times N, essentially to calculate the number. So we'll see that in a second. Okay, so we've added this. All right. So now let's compute, or let's have the values for it. And then we need to define the operations that will allow us to calculate this. So here we have instantiate generator. This is Bitcoin gen. So it's going to take a point G, which is this G over here that we had already defined. So that's our starting point. Okay. And then we have the value n. So the order of G is known and can be mathematically derived. So this is a parameter. Think of it as we multiply G times n, right, in some way. So and that's an operation that we have to define. All right, but that's essentially so that we can, from G, get another value. So we've done that. So we create Bitcoin gen by instantiating the class generator. So the private key, which we're going to be referring to as the secret key here, is simply a random integer that satisfies some condition of being between 1 and n. Okay? So here, let's calculate secret key first. So how do we do that? Let's grab this one here. So it's some integer, but notice how it's calculated. There's a funny story about this. So notice, we're going to create an int from bytes, and then notice here, this is like a password or a passphrase, right? So Andresh is cool, and some, emoji, right? An emoji. This is how you will create your initial secret key, just some random integer. So this is how you start. You create a password, a passphrase, usually on Bitcoin, and that's your starting point. That's going to be converted into an integer, and from there you start building things. Okay? So lots of people, when they got their Bitcoin initially, when it wasn't worth a lot, if you remember, they did this, right? They created, put their name or whatever it was, and generated the secret keys and everything, and then they had it in flash drives, I think, and then they threw away the flash drives. And when Bitcoin went really up, right, in value, then they were looking for these. They would go to landfills and things looking for these, because if they found those, they could retrieve their wallet and get their money. All right, so it starts here. This is the beginning of your identity for your secret key. So think of it as creating a private key, and then from here a public key, and all of that. So some value that you create, some number. But in this case, we're creating it based on a specific string, such as this one. Okay, so I don't know if you guys are following along, but if you are following along, you should be able to get the same number from this. Okay, so secret key, I'm going to print it out. Okay, so there it is. That's the number that you get initially from that initial string. Okay. All right. Now we want to assert that it does meet the condition of being within n. So n is in Bitcoin gen, so we define n to be this. So we're going to do an assert, right, just to make sure that secret key, this value that we just created, is within 1 and the n that we define here. So assert just, if it doesn't error out, it means it's true. So there's no issues. Okay, so it does meet the condition. All right, so we have that. So let's analyze it. So I have this number starts with three twos, and ends in 144, ends in 144. You guys see that, right? So this is our secret key, or private key, if you want to call it that. Very unassuming integer, right? But anyone who knows it can control all your funds, all of the funds you own on the Bitcoin blockchain, right? So this is what gets at the beginning of your wallet and getting access to everything, your identity. So in its simplest form, or most common vanilla use case of Bitcoin, it is the single password that controls your account. Okay? We are now going to generate a public key, which is where things start to get interesting, right? And you guys understand public-private key work together. Here we have a different procedure because it's based on elliptic curves, but essentially it's this idea that from the private key, we create a public key. So what is this public key? So the public key is the point on the curve. So remember, we start with a point on the curve. Now we're going to get another point on the curve. But the public key is the point on the curve that results from adding the generator point to itself secret key times. You guys see that? So secret key is an integer, right? And we have a G, right? We also have that, which is a point. So public key is the point on the curve that results from adding the generator point to itself secret key times. So here it is. So I have my, i.e. public key is being calculated. It's essentially adding G, the point G, G plus G plus G. How many times? Secret key times. Got it? So equivalent equal to secret key times G. All right, these operations, of course, are not normal operations, but they're operations on the curve itself. Right, so that have to be defined. Now, the secret key is an integer, right? You guys agree? You just saw it, and but the generator point G is an x and y tuple, right? Which we have seen. That is a point on the curve, resulting, obviously, in an x and y tuple for the public key, okay? Which is, again, on the curve, which makes sense, right? G is a point, G is a point, G is a point. We just do that n times, or secret key times, but essentially is a point, 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 so it produces a point. All right, so as I said, the secret key is an integer, but the generator point G is an x and y tuple that is a point on the curve, which results in an x and y tuple public key, which again, a point on the curve. So of course here, we have to define these operations, addition, and so on. I'm just going to bring in the functions for this, as they can be a little bit complicated. But nicely, this is written from scratch. And so you guys, if you feel like it, you can explore in depth, how these are implemented, okay? So here we are. Notice all this code here is actually the addition that we just described, because it's an addition on the curve. So I'm just going to copy this into my code. But some of these ideas will be familiar to you already. So we go over here. Okay, so let's take a look a little bit. So we have, we're going to define an infinity point as a special point at infinity, kind of like a zero. So just think of it as some constant that we have to look at, okay, in the algorithms. Notice that the algorithm includes the extended Euclidean algorithm. That should sound familiar, right? Right? You've seen this before? RSA also had this algorithm, right? So once again, you are using some of these ideas. We have modulo operations going on, so it makes sense. So we have a Euclidean, extended Euclidean algorithm. Remember the inv? We also saw this in RSA, right? So that function is also there. And then we have a function here called the elliptic curve addition. So again, it's not a normal addition. That what we were doing is an addition that would happen geometrically in the curve. Okay, so we're just going to use these, but as key points to consider. This function, elliptic curve addition, is using inv. Do you see that? So it's using inv, and the inv function over here uses the extended Euclidean algorithm, which is what we defined up here. Okay, so that is the definition from scratch of adding points on this curve. So once that function is done, elliptic curve addition, we can conveniently add a special operation to the point. You can see that there. So we're just going to say point.add. So whenever we do an addition or we invoke an addition for the point, we essentially just call the function that we just defined, which is called elliptic curve addition. So this is just a nice way of you defining a new operation for your points in Python. Make sense? All right. So we define a new type of addition, not like our normal addition, but an addition for elliptic curves. Okay. And you can see is quite involved. So now point was, we had defined this here somewhere. Point in the class, right? Class point. So we can define this operation now for us to use. So let's go ahead and run that. Okay. So all of that so that we can add the G's. So the important thing to note here is that everything is just a bunch of adds and multiplies over the tuples x and y. Okay? With some modulo p sprinkled everywhere in between. Right? So you guys are familiar with modulo operations already, so that's what's in these algorithms. So let's try it out and just see how it works. So the idea now is we're going to be computing public-private key pairs, right, that we can start to use for our identity with the goal of creating some type of wallet ID. All right, so let's do one example here. I'm going to grab this code. Just so now, and we can do these kinds of things. So this is going to be, if our secret was the integer 1, right, so 1, then our public key would just be G, right? So it's 1 times G. So secret key, public key is going to be PK X and Y. And then we want to verify that this public key is on the curve by doing the same y squared minus x cubed minus 7 modulo prime. All right, so we run that one, and you can see it is true, and that is essentially the public key that we calculated from the secret key. Notice there was no need to use the add operation, right? Because there was only 1. However, by definition, remember the definition over here, this one, right? So the public key is the point on the curve that results from adding the generator point to itself secret key times. There was only 1 for secret key, so just G was fine. But in the next one, it'll be 2 or something, so now it's like 2 times G. But we don't have a times yet. We only have add, right? So we need to define that operation as well. So let's go ahead and try out another example here just to kind of, to derive the point. Okay, all right, so if it was 2, so my secret key or private key is 2, the number 2, then what is public key? So it's going to be G plus G because it's 2G. All right? So here you can see that the public key is just G plus G. Right? But this plus, what is this plus? This plus is, who can tell me, what is this plus here? It's not a regular plus. It is this thing, right? What I just defined here which is essentially invoking this function, which invokes all of that code. So it's the actual plus or addition on the elliptic curve. All right, so here you can see k equal to, so public key should be g plus g, right? And so now we can look at what it is and also if it's on the curve or not. So it is on the curve, and there's your public key, which, as you can see, it is in fact a tuple of the coordinates. Any questions? Obviously, I'm using very simple examples here just for illustration, right? Our secret key, as we saw before, was much larger, calculated from our string or whatever it was. Any questions so far? All right, so let's go ahead and take a look at another example here. So we're going to do, what if our secret key is 3? Okay. So I'm going to do SK3. So now the public key is what? G plus G plus G, which is equal to saying 3 times G. But remember, we can't say 3 times G because we haven't defined that operation yet. We've only defined the addition operation. So now we can look at PK, the x and y coordinates, and of course we can check if this value is on the curve, and we can see it is indeed on the curve because it's true, and that is your public key x and y given your initial secret key. All right, so hopefully that makes sense. So now we are, pretty good, right? And we see all these values. Now we can implement also this. I'll do more quickly, but this is just the same thing that I did for plus, but now the multiplication. So you don't want to do g plus g plus g plus g, especially because your n is going to be gigantic, right? So that would not be efficient. So we need to have a multiplication approach. All right, and so we're going to do this one here, but it's the same idea, just multiplying. So here, this is the double and add. Notice here, point.rmul. So we're creating so that we can, the symbol of multiplication. Now we'll use this function instead. All right, and we'll skip the details of this because this is just the logic of this multiplication on the curve. But let's go ahead. Once we have it, we can do some comparison, right? And so g should be 1 times g. Now this asterisk here, this multiplication, is essentially that, correct? So that's what's happening. But obviously g, this is our previously defined addition operation, and this is our new operation of multiplication on the curve. So obviously g plus g should be equal to 2g. G plus g plus g should be equal to 3 times g as elliptic curve operations. So let's try it out. And I think, yeah, I ran that. So if I run these, they should be true. Perfect. And they are true. All right? So there you have it. So now we have a convenient way of calculating our public key from our private integer key. So now let's do this correctly, right? So we had a secret key. So let's grab the secret key. So far, notice I've been using 1, 2, 3, right? But our secret key was not 1, 2, 3, right? It's a really large number. So obviously we need the multiplication now. So I'm going to grab, first I'm going to do the calculation. So notice to calculate the public key is just equal to the secret key, this one, times g, the point. All right? Using our curve multiplication approach, elliptic curve. Sorry. All right, so I've calculated the public key. Now we can do the same. Print the values and make sure that it is on the curve. So it is true. That means it is on the curve, and there you have it. This is actually now your public key. for an elliptic curve. Make sense? So now there you have your secret key, you have your public key, and you have that the public key is a point on the curve. All right, that's how elliptic curves work. All right, as far as creating your credentials and things like that. So with the private and public key pair, we have now generated our crypto identity, and you guys know this, right? So that's usually something useful. So from here, then, now that you have this public and private key that are your information, you would want to create a wallet, right? And the wallet is quite simply an ID that's going to live on the curve, right? Derived from the curve, and so that's something that's in the blockchain now. That's you. And then whenever you let's say do a job and want to get paid in Bitcoin, somebody would issue a transaction and send you Bitcoin to that wallet, and boom. You see that? And then when you pay somebody, then you move funds. That's the idea. Excuse me. So now it's time to derive the associated Bitcoin wallet address. So that's the next thing that we're going to do, and we're going to be using, shouldn't surprise you, hashes. Once again, hashes, right? It's always hashes. So the wallet address is not just the public key itself, very important. So the wallet address is not just the public key itself, but it can be deterministically derived from it and has a few additional parameters, such as a checksum and so on. Before we can generate the address for the wallet, though, we need to define some hash functions, okay? So Bitcoin uses the ubiquitous SHA-256 and something else called RIPE-MD160. But you guys are familiar with SHA-256. And here is the SHA-256 implementation in pure Python, right? So if you've ever wanted to see that in like pure Python from scratch, here it is. And this is based on the description at the NIST. All right, so this is a SHA-256 implementation, so I'm not going to go into the details of it. I leave that to you guys if you're interested. So let's just copy it. So SHA-256. So it's quite involved. I think I grabbed two things there. So I'll move this part down. So again, all this is the implementation of the SHA-256 function. So you can see it's essentially a very involved function. Do you see that? But that's SHA-256. All right, we've been using it all semester, but this is just the implementation. You can see there's some shifting of bits and things like that, rotations and things of that nature. All right, so let's run it, see if it gives us an error. Did I click on it? All right, so we got a green check mark, so that means it ran fine. So now we have it in memory. Okay, so we can try it out. Okay, so it's a function that takes, we create a little variable called SHA-256. All it's doing is it's calling this function, right? So we're like linking it, and then it takes in a value. So for instance, here this is going to be an empty hash, right? There's nothing in there. So I'm going to move this down. Okay, so that's an empty hash. It should look like that value, E3, whatever it is. Okay. Then here is a random bytes message. You can put your name there, whatever you want, and invoke SHA-256. So it's just giving us the hash via the SHA-256. Now the number of bytes in SHA-256 should be 32, right? So that's the answer that we're getting. Any questions, guys? All right, so that's we just need this function, SHA-256. We're also probably going to add the other one. Yeah, and then this, the reason why the SHA-256 was implemented here is just to show you kind of how it works. There's no mystery, but you guys, already had an idea of that. SHA-256 takes some bytes message that is to be hashed. It first pads the message, then breaks it up into chunks, and passes these chunks into what can be described as a fancy bit mixer, like XOR. That's what I mean by, bit mixer is XOR type of thing, that contains a number of bit shifts, binary operations, but that results in the beautiful properties of the security of SHA-256. So as you know, it creates a fixed size, random looking short digest of any variable sized original message. So this is the definition that our working definition of SHA-256. And then this is all the information you guys know already about SHA-256. So Bitcoin uses SHA-256 everywhere to create hashes, okay? And of course, this is the core element of this idea of proof of work, right? So we already described, you're constantly hashing, measuring the security of the hashes, and that essentially provides the integrity. Others in the distributed cloud, or whatever you want to call it, are doing this, as we discussed with the miners. And where the goal is to modify the block of transactions until the whole thing hashes to a sufficiently low number, okay, which is, involves being secure, okay? And I already described this. All right, so the next part is the same thing. We're going to have this other algorithm called ripe MD160. This is another hash function that the Bitcoin uses, or blockchain. So I'm just going to add this one here. So as you can see, pretty involved functions. For hashing. So these are hashing. Okay, here we are. So we'll add this one as well. Ripe MD. Okay, so we got a green check, so that function has been added. So now we can just try it out as well, get a sense of what's going on. I'm going to copy this. All right, so just like before, we create a variable ripe MD160. We associate it with our previously defined function. Then we take a message, hello, this is a test. We run it through ripe MD, and it's going to give us a hex digest, and we can calculate the number of bytes, which is 20 in this case. Okay. So, yeah, that's essentially the idea. And then we're just going to create a class so that we can start to create the final ID or account. Yeah, the same description of the function, so I'll skip that. All right, so we're finally ready to get our Bitcoin address, right? So that's the Bitcoin wallet, so we need to define that. We are going to make a nice subclass of point called public key, which refers to the point on the curve, but it'll have some additional semantics and interpretation of a Bitcoin public key, and some methods for encoding and decoding the key into bytes for communication via the Bitcoin protocol. And this exists because it's very common, for instance, to get wrong 0 versus the O, right? How many times you type O and it was a 0, or you type 0 and it was an O? You know what I mean? Well, Bitcoin is dealing with money, right? You don't want to think you typed a 0 and then it was an O, and so they created an encoding that avoids those kinds of problems. That's essentially what it is. All right, but let's grab this one. And these are going to be just some functions that will allow us to do this encoding. I think it's called B58 encoding. All right, and it's a special type of an encoding. All right, so there's going to be a function in here to calculate the address, a function in here to do the encoding, and and some information about the point. So here we are. So I've instantiated that one. We're almost done with this. All right, so we're gonna try this class, okay, that we just defined. Okay, we will define the B58 alphabet, I think. This is a Bitcoin-specific encoding of bytes that uses something called base 58 of characters of the alphabet that are unambiguous in what I just said. For example, it does not use O and 0, okay? Because they are very easy to confuse or mess up. So we have to take our Bitcoin address, which might be like 25 bytes in raw form, and convert it to this base 58. Okay? All right, so let's create this function for B58 encode and provide an alphabet for it. And hopefully we'll be ready to create the wallet ID, given our public and private key. So let's try to, now let's go ahead and create our wallet, our address. So how do we do that? We essentially take our, so let's see here. We're going to print our Bitcoin address. And this is not going to be happening on the way the code is written. There's two environments, one for development and one like the real environment, right? So because you would be essentially with this code creating an ID, right, that could exist in the actual Bitcoin world. So this is just a test scenario, but you can see you take in your public key, right? You load it in there, and we already created this this class that takes in the public key and adds these functions, such as this function to calculate the address. Okay, so we'll come back to this in a second just to see how the address is calculated. But you can see we had a private key. What did we do with that private key? We calculated a public key. Remember that? And then from that public key now, what are we calculating? The ID. And this ID is the wallet ID. Okay, so let's, so you can see from public key, we calculate address, and now we print it. And there you are. That's your Bitcoin address that people would use as reference to send money, but generated from your public key. So we're almost at the end. So we'll have a little summary here, but let's try this, a full example. Right? To kind of summarize. So secret key was the first, just an integer, right? And then we take G times secret key to produce our public key. So in this case, my secret key is 1, therefore my public key is what? Secret key times G. Do you all agree? Yeah? All right, good. And then now I have a public key, so I load the public key here, and then from it I calculate the address, and now I just print the address. So there you have it. That's the full pipeline. Okay. Okay, so we have that. So in summary, and we can just summarize it here, we are able to generate a crypto identity that consists of a secret key, which is a random integer that only we know, derived from some password or something like that, and a derived public key by jumping around the elliptic curve using a scalar multiplication of the generating point on the Bitcoin elliptic curve, right? So we define these functions for moving in the elliptic curve. And again, that it works, like, that's right. So that's the security of it. So we have a secret key from some password, and a derived public key by jumping around the elliptic curve. We then derive an associated Bitcoin address, which we can share with others to ask for money, and doing so involve the introduction of the two hash functions for SHA-256 and so on. So here let's summarize this one final time, and then we still need to dive into that how to calculate the ID. So we'll look at that in a second. But let's look at the functionality. So our first Bitcoin identity, our actual secret key was that very long number. So if you remember, just to remind you guys, let me move this down a little. So secret key was a number that number, right? You remember all the twos, and it ended in 144. The public key had our X and Y. Right, so that's our public key. And then we can calculate our address, right? Did we calculate this already? Yeah, public key, we did that. All right, so we have the address, and there you are. Makes sense? So this is the identity. You can see it's very similar to everything we've been doing, just based on these algorithms. All right, so that's the summary. That's as far as I was going to get with this. The only thing is we still need to dive into here. No, not here. Sorry, this function, right? So we need to dive into here. So we know that we grab the public key, and from the public key, we need to do some encoding, but also we perform this, right? The calculation of the address. So encode the public key. So here we can see this returns the associated Bitcoin address for this public key as a string. We encode the public key into bytes and hash to get the payload. So you can see here, we do self-encode. What is self? Public key, right? So we encode public key. So now it becomes PKB hash. Okay. We have these version parameters that are added to PK hash to become version PKB hash, and then guess what? We take some hash value of it, right? So SHA-256 version PKB hash, right? And then so then we calculate this byte address, we encode it, and then we return it. And when we did the encode here, where is that? Self-encode, right? This self-encode was actually this one over here. And notice that what it returns is the PKB after being hashed with SHA-256 and then hashed with ripe MD. Do you guys see that? So essentially, you can think of it as grabbing the public key, doing some things to it, adding some prefixes, etc., and then that final string is hashed to produce RID. Any questions, guys? No questions? All right, so yeah, so that's essentially the whole thing. So we take the public key, add data to it, and then hash it. All right, and that value is returned, and it produces, well, as we saw, your Bitcoin address derived from your public key, and that essentially is your wallet ID. From there, of course, there's still a lot, you still have to learn the transactions, but there's like a coding a format that they use for transactions and things like that. But we'll see. I leave it to you guys. If you guys want to learn more about it, you're welcome to go through the Jupyter Notebook, and it talks about obtaining seed funds and getting into more of the details of it, or you can take the course later, in your studies. All right, so this is a good stopping point, so I'll stop the video here.